While the world watches the skies for 3i Atlas, the mysterious interstellar traveler, something far closer and far quieter is moving our way. It's not glowing bright in the headlines. It's not trending on social media, but it's real, and it's coming fast. Astronomers just confirmed a new object, one they nearly missed, flaring and fading in strange bursts as it races toward its closest pass by Earth. Why did we spot it so late? What is it hiding behind its flickering light? And why does it seem to break every pattern we know about comets? This isn't a story about panic. It's a story about perspective, about how even in a sky full of data, we can still be caught off guard by what's right in front of us. Stay with me until the end, because the truth behind this quiet visitor might change how you see Earth's place in the universe. The sky has always spoken to us, quietly, in ways we often take for granted. It hums with the slow rotation of planets, the measured pulse of stars, and the occasional flash of wandering comets that leave behind whispers of ice and rock. Most nights it is calm, almost predictably silent, but sometimes the silence itself becomes a signal, a subtle disturbance that hints at something moving just beyond our understanding. And tonight, as the headlines scream about 3i Atlas, the mysterious interstellar traveler passing through our cosmic neighborhood, there is a quieter, subtler warning being missed. Something is coming, something the world is barely noticing. For decades, humanity has trained its eyes and instruments to scan the heavens, watching for objects large and small, mapping their movements and predicting their paths. Space agencies, universities, and amateur astronomers alike contribute to a vast network of observation, cataloguing every flicker and flash in the night. And yet, for all our technology, all our telescopes, and all our meticulous records, the universe remains elusive. It reminds us, almost mockingly, that no matter how far we advance, there will always be gaps, blind spots in our perception, shadows in the glow of the stars. The quiet comet we are about to speak of first appeared in these shadows. It wasn't blazing across the sky in a spectacular display, nor did it announce itself with a long tail glittering in the sunlight. Its arrival was subtle, almost shy, like a guest slipping quietly into a crowded room. It flared for moments, then dimmed again, a flicker easily overlooked by those whose attention was consumed by brighter, more famous phenomena. It arrived during a time when the eyes of the world were fixed firmly on 3i Atlas, a cosmic celebrity, a visitor from beyond the solar system, a spectacle so compelling that even the most seasoned astronomers found themselves captivated. And in that distraction, the smaller, quieter, and more unpredictable objects slipped past. Imagine for a moment the feeling of standing in a vast observatory, a room filled with screens, monitors, and telemetry readouts. A scientist notices a tiny blip, almost imperceptible, at the edge of one screen. It comes and goes within seconds. At first, it seems like a glitch, perhaps interference from a satellite or a passing cosmic ray. But then, when the same anomaly appears on another instrument, in another location thousands of miles away, the pattern cannot be ignored. There it is again, persistent, fleeting, and yet real. Something is moving through our solar system in a way that doesn't follow the script we expect. Something that refuses to announce itself in bold strokes and bright trails. This is the paradox of discovery in the modern age. The louder, more spectacular objects grab our attention, while the subtler, equally significant phenomena are left to the edges of perception. We have trained ourselves to notice the extraordinary, but in doing so, we risk missing the quietly extraordinary. This comet, small, dim, unpredictable, embodies that truth. It is a reminder that vigilance is not measured only by what we see, but also by what we fail to see. As the world debates the trajectory of 3i Atlas, social media buzzing with speculation and news outlets racing to explain every new image, the quiet object moves undisturbed. It does not respond to our timelines, our hashtags, or our theories. It follows a path dictated by gravity and inertia, by forces far older than humanity itself. And as it does, it presents a subtle challenge. Are we capable of noticing it in time? Are we prepared to observe what does not announce itself loudly? In these moments, one realizes that space is not a silent void, simply because we choose to perceive it as such. Silence in the cosmos is active. It holds information. It carries the weight of absence, the significance of the unnoticed. Every comet, asteroid, and asteroid fragment has a story. Every faint glimmer may be a messenger from deep time, a remnant of a solar system in constant motion. And this particular visitor, though nearly invisible against the vast canvas of the sky, is about to teach us just how fragile our certainty can be. We often romanticize space exploration, thinking in terms of grand missions, interstellar travel, and dramatic discoveries. Yet the true drama often unfolds quietly, in the subtle deviations, the small anomalies that escape our notice until they cannot be ignored. The world at large is not paying attention to this comet because it does not yet seem threatening. Its path does not intersect Earth, not in the immediate sense. But the significance lies not in collision nor in spectacle, but in revelation. It exposes the limits of our observation, the blind spots in our planetary defenses, and the humility we must maintain when watching a universe that moves at its own pace. And here, in the stillness, is the first lesson of tonight's story. The universe speaks not only through what it shouts into our gaze, but also through what it hides in the quiet. To understand the cosmos, and to understand Earth's place within it, we must learn to listen to both. We must train our attention not only on the bright lights that dazzle, but also on the faint signals that persist quietly at the edges of perception. Only then can we appreciate the full narrative of our solar system, the hidden movements of objects that carry histories longer than any human civilization, and the subtle threats and wonders that quietly shape the space around us. As the comet moves closer, its presence a whisper against the roaring fame of 3i Atlas. We are reminded of a timeless truth. In a universe so vast and so old, the most important stories are not always the loudest. Sometimes the quietest events carry the deepest weight. Tonight, we will follow that quiet story, tracking its journey, exploring its mysteries, and learning from the way it slips past our gaze. And in doing so, we will understand not only the comet itself, but also the delicate balance between observation, attention, and the mysteries that wait just beyond our perception. So stay close, listen carefully. The silence is speaking, and for the first time, we are learning how to hear it. In the quiet pre-dawn hours, the world seems asleep, but the sky is awake. It stretches above us in infinite darkness, speckled with stars that have traveled light years to reach our eyes. This is the time when discoveries often happen, not in the glare of headlines or the flash of social media, but in the patience of those who watch attentively while the rest of the world dreams. And it was during one of these quiet nights that the comet we now follow was first noticed. The initial observation wasn't the result of a grand, government-led mission or a high-budget telescope stationed in space. No, it was something far more modest and human. A small, automated telescope array in northern Chile, designed to scan sections of the sky for minor objects, for things that might otherwise slip by unnoticed. It had been quietly observing the stars for years, recording data, creating mountains of charts and logs that very few would ever examine closely. It was here, amidst countless routine readings, that a fleeting anomaly appeared, so brief that at first it seemed almost like an error. A flash of light, lasting barely a few seconds, flickered at the edge of the detector, bright then gone, blinked once then vanished. To most, it would have been a glitch, a random artifact in the data caused by cosmic radiation or electrical interference. But the trained eyes of the astronomers monitoring the array saw something different. There was a pattern to it, subtle and almost imperceptible. Another instrument confirmed the signal, slightly offset, but unmistakably present. Something real had passed by, unnoticed until that very moment. The beauty of accidental discovery is that it cannot be anticipated. You cannot schedule surprise. The telescope array had been programmed to sweep methodically across the night sky, not to predict when an unannounced object might appear. And yet, there it was, flaring for just long enough to be caught, and then fading back into obscurity. The comet's arrival was unplanned, unexpected, and completely out of sequence with the carefully mapped expectations of astronomers. When the first readings were confirmed, a sense of cautious excitement spread quietly through the observing team. They were aware that even the smallest comet could provide crucial information about the solar system's history, the dynamics of celestial objects, and potentially the vulnerabilities of our planet's observational networks. But more than that, they felt the thrill that comes with being the first to witness something new, something that had traveled billions of miles, unobserved, to reach this corner of space. This was not an object that demanded attention with a long, bright tail or the kind of dramatic glow that fills headlines. Its arrival was understated, almost shy. Its brightness was inconsistent, flaring unpredictably, teasing detection, and then retreating again into invisibility. It was the type of discovery that requires patience and persistence, qualities that the modern world increasingly undervalues. While everyone else was focused on the Interstellar Visitor 3I Atlas, this quiet intruder was already moving through the solar system, revealed only by the vigilant observation of a few dedicated individuals. The comet's path, although initially uncertain, began to reveal itself through repeated measurements and careful triangulation. Its speed, trajectory, and behavior could be partially inferred, but many questions remained. Was it a remnant of a larger object that had broken apart long ago? Was its irregular brightness a sign of fragmentation, or something entirely unknown in its composition? Each new piece of data seemed to answer one question while raising several more, and in that uncertainty lay the magic of discovery, the intimate connection between human curiosity and the unknown vastness of space. It is worth pausing to consider how easily such an object could have been missed entirely. With the sun's glare masking certain angles, the limitations of telescope coverage, and the sheer scale of the night sky, many potential comets go unnoticed for years or decades. Some objects are only found after they pass Earth, leaving scientists to reconstruct their paths retroactively. This accidental discovery is a reminder that space does not yield its secrets willingly. It requires vigilance, timing, and sometimes sheer luck. The team in Chile, aware of the comet's unusual behavior, immediately began cross-referencing their findings with other observatories. Amateur astronomers in Europe and North America were alerted, as were several university-based observation programs. Each independent confirmation strengthened the understanding that this was not a random fluke or a sensor error. It was real, it was present, and it was moving closer to Earth's orbit, faster than anticipated. There is a human element in these accidental discoveries that is often overlooked. The astronomers involved were not seeking fame. They were pursuing the pure joy of knowledge. They worked quietly, sharing data across digital channels and forums late into the night, coordinating observations and discussing theories. There is a certain humility in realizing that, despite all of humanity's achievements, the universe still holds surprises that slip past even our most sophisticated instruments. Meanwhile, the world outside remained largely oblivious. Headlines screamed about other, more spectacular celestial events. 3I Atlas dominated social media, YouTube videos, and news cycles. The comet's subtle presence went largely unnoticed, a reminder of how much of reality exists outside the public gaze. Often, the most important discoveries are the quiet ones, those that unfold without fanfare, without urgency, and yet carry implications far beyond their initial observation. Accidental discoveries like this one are what push science forward. They remind us that the universe is vast, unpredictable, and uncooperative. They challenge our assumptions, our preparedness, and our understanding, and they reveal the fragile balance between observation and ignorance, attention and oversight. The comet's flaring light, caught by chance, becomes a symbol, a fleeting moment of insight into a system much larger than ourselves, a universe that will continue its dance regardless of whether we are ready or not. And so, the quiet visitor continues its journey unnoticed by most, but now on the radar of those who understand the significance of chance. It teaches patience, humility, and attentiveness. It shows that sometimes the greatest revelations arrive not with a bang, but with a whisper, a flash that might have been missed if not for the sharp eyes of those who refuse to overlook it. As we follow this comet in the chapters to come, we will uncover its secrets, trace its path, and learn what it reveals about both the universe and ourselves. This discovery, born of chance, is just the beginning. It reminds us that the universe is vast, mysterious, and always moving, and that sometimes the quietest signals carry the loudest lessons. In the vast cosmic theatre, timing is everything. Planets revolve with precise, predictable grace. Comets and asteroids trace their elliptical paths like dancers rehearsing an age-old choreography. And yet, every so often, an object appears late, arriving without warning, slipping into the scene at the very moment we least expect it. This is the story of the comet that emerged quietly into our solar system, appearing just as humanity's attention was fixed elsewhere, lost in the spectacle of 3I Atlas. Its late arrival was not merely inconvenient, it was a profound reminder of how small and fragile our perception truly is. When astronomers first reviewed the data from the Chilean observatory, they realized that this object had been on its journey for millions of years, yet it had only just now crossed into the range of our detection systems. Its trajectory suggested it had come from the distant reaches of the outer solar system, perhaps even the Oort cloud, that far-flung reservoir of icy bodies that marks the boundary between known planets and the unknown darkness beyond. And for all this time, it had remained unseen, silently moving toward the inner solar system, oblivious to the buzz of human attention. The late detection presented immediate challenges. Unlike objects tracked for months or years, allowing scientists to calculate their paths with high precision, this comet had entered our awareness with very little prior observation. Predicting its future position, speed, and behavior was now a race against time. Small variations in its movement, a sudden flare, a fragment breaking off, a gravitational nudge from a planet, could significantly alter its trajectory. Every observation mattered, and the window for gathering data was shrinking. What made this late arrival so unnerving was its unpredictability. While 3I Atlas had been closely monitored for weeks, providing a wealth of images and measurements, this comet behaved erratically. Its brightness varied, sometimes flaring sharply and then fading to near invisibility. Instruments that measured its composition suggested it contained volatile ices that could sublimate suddenly, creating bursts of gas and dust that acted like natural thrusters. Each flare changed the dynamics of its flight, rendering previous calculations only partially reliable. In other words, the universe had handed scientists a problem that required both patience and improvisation. An object arriving late, demanding immediate attention. The late arrival was also a lesson in human perception. We are conditioned to focus on what is already visible, what has already made a name for itself. Headlines, social media trends, and scientific press releases all direct our attention to familiar names and objects. 3I Atlas, with its interstellar fame, captured imaginations worldwide. Meanwhile, smaller, less spectacular objects, those that arrive quietly, without fanfare, risk going unnoticed until their presence becomes impossible to ignore. This comet was such an object, small in scale, late to the spotlight, yet carrying potential consequences that required immediate consideration. The implications extended beyond mere observation. Our planetary defense systems, designed to monitor for hazardous objects, rely on early detection to allow for preparation, intervention, or mitigation. When an object is detected late, the available response window shrinks dramatically. contingency plans that assume years of lead time are suddenly compressed into days. The comet's late arrival became a stress test for these systems, a reminder that even with all our technology, the universe has a way of highlighting our vulnerabilities. Amateur astronomers quickly became critical allies. Equipped with modest backyard telescopes and shared global networks, they supplemented the observations of professional facilities. Each new image, each recorded measurement, helped refine the comet's projected path. In a sense, the late arrival democratized attention. It required the vigilance of both experts and enthusiasts alike. The cosmos, in its unpredictability, invited humanity to cooperate in a way that transcended headlines and fame, emphasizing observation over spectacle. The late arrival also had a psychological impact. People are not accustomed to thinking about cosmic threats in days, only in months or years. Suddenly, the idea that an object could approach Earth so swiftly, unseen until just days before its closest pass, triggered unease, curiosity, and fascination. It was a reminder that the universe operates on its own timetable, independent of human convenience. The comet's schedule was not ours, yet we had to respond in time with the resources and knowledge available. Interestingly, this late detection revealed much about the comet's nature. Its flares, inconsistent brightness, and erratic movement suggested a body more dynamic than ordinary, perhaps a fragment of a larger parent body, or an ancient relic from the outer solar system disturbed from its long sleep. Each observation raised further questions. How long had it been traveling silently? What forces shaped its unpredictable behavior? Could it reveal new information about the early solar system? Or even the mechanisms that govern cometary evolution? The contrast with 3I Atlas was stark. One object, heavily observed and documented, dominated attention with its interstellar origin. The other, small, late, and almost invisible, moved through the same space largely unnoticed. It was a humbling lesson. In the grand theatre of space, fame and attention mean nothing. The universe operates independently of our interest. Discovery is not always the loudest or most dramatic revelation. Sometimes it comes quietly, as it had in this case, with subtlety that requires patience, focus, and humility to appreciate. And yet, as the comet continued its journey inward, it revealed a profound truth about human observation. Timing is everything, and late arrivals can carry consequences far beyond their apparent size. They challenge assumptions, stretch resources, and demand adaptability. They remind us that vigilance is as much about noticing the small, subtle events as it is about monitoring the grand, obvious spectacles. The universe does not announce its most important lessons with trumpets. Often they arrive quietly on schedule of their own making, leaving us to notice or to miss them entirely. As we follow this comet, the story of its late arrival becomes the foundation for everything that comes next. Its timing, subtle movements, and unpredictable flares are not just astronomical data points. They are narrative threads that bind the story together, teaching lessons about observation, curiosity, and the fragile balance between certainty and the unknown. In the chapters to come, we will see how this late arrival interacts with the solar system, how its behavior informs our understanding, and why even small, unnoticed objects can carry significance far beyond their apparent scale. Tonight, we recognize that discovery is not always intentional, and attention is not always guaranteed. The universe has a rhythm that operates independently of human schedules, headlines, and obsessions. And in the quiet wake of this comet's late arrival, we are reminded to watch, to wait, and to learn. Because sometimes the most important revelations come to us precisely when we least expect them. The universe has a way of testing our attention. For centuries, humans have looked up at the night sky with curiosity, awe, and sometimes fear. We have catalogued planets, tracked asteroids, and even sent spacecraft to distant worlds, all in the hope of understanding our place in the cosmos. Yet despite these achievements, space has a way of reminding us that we are always watching just enough to notice, but often too little to anticipate. And now, the quiet comet, late to our awareness and flaring unpredictably, begins to reveal itself not just as a curiosity, but as a potential threat. When the initial measurements were refined, the data began to show patterns that were impossible to ignore. The comet's trajectory, previously estimated with caution, indicated a closer approach to Earth than initially assumed. Though not necessarily catastrophic, the proximity was enough to command attention from planetary defense teams and astronomers alike. Even a small object traveling at high velocity carries immense energy, and an impact, however unlikely, could have significant consequences. It was at this moment that the abstract became real. The comet was no longer just an object passing through space. It was a reminder that cosmic danger exists quietly, often unseen, until the last moment. The first question scientists asked themselves was straightforward but urgent. How could we have missed this? Advanced telescopes, monitoring networks, and automated tracking systems exist precisely to catch these objects early. Yet here was a comet, flaring unpredictably, appearing suddenly in the observational window, and moving in a way that defied easy prediction. The answer lay partly in scale and partly in distraction. Humanity's gaze was fixed on 3I Atlas, an interstellar object capturing imaginations and headlines worldwide. Meanwhile, the smaller, quieter comet slipped into our awareness, almost as if hiding in plain sight. Its behavior was unusual. Unlike typical comets that display relatively steady brightness as they approach the sun, this one flared intermittently, sometimes doubling in luminosity within hours, only to dim again. Scientists quickly realized that these flares were not merely optical curiosities. They reflected real dynamic processes on the comet's surface. Ice pockets sublimating, dust ejections, and possibly fragments breaking free created unpredictable changes in its trajectory. Each flare was a natural thrust, subtly altering its path and complicating predictive models. The threat, it seemed, was not only proximity, but also unpredictability. The public, of course, remained largely unaware. Social media and news channels continued to focus on 3I Atlas, a spectacle of interstellar travel and cosmic mystery. Few outlets mentioned the small, late-arriving comet approaching Earth. And yet, the threat it represented was no less real. The scientific community faced a delicate balance, informing the public without causing panic, while simultaneously refining calculations and observing every flare. It was a reminder of the tension between transparency, responsibility, and human psychology when dealing with potentially alarming discoveries. Planetary defense teams mobilized, though quietly. They coordinated with observatories across the globe, issuing alerts and requesting rapid observations. Every telescope capable of detecting the comet's light was tasked to monitor it, and every measurement counted. Scientists calculated potential closest approach distances, velocities, and the effects of solar radiation on its path. Models were run, simulations performed, and contingency plans drafted. The universe had issued a warning, subtle, yet unmistakable, and humanity was forced to respond in real time. What made this situation compelling, both scientifically and narratively, was the combination of magnitude and subtlety. Unlike asteroid impact scenarios predicted years in advance, this comet arrived late, small, and almost invisible. It tested our observation systems and our cognitive biases. We tend to notice what is loud, dramatic, and widely discussed, while the quiet threats, the ones that require meticulous attention and patience, can slip through unnoticed. Here, the universe was offering a lesson. Danger is not always flamboyant. Sometimes it whispers, and only the attentive can perceive it. The comet's threat also illuminated a deeper, almost philosophical point. Humanity's obsession with spectacle can blind us to subtler truths. We are captivated by grandeur, interstellar visitors, massive storms, spectacular images of distant galaxies. But the quiet, less glamorous phenomena, the small comet appearing unexpectedly, flaring briefly, moving unpredictably, are often the ones that carry consequences far closer to home. It was a cosmic nudge, reminding us that perception and attention are as vital as technology. In the following days, as the comet moved along its path, every flare became a headline among scientific circles. Amateur astronomers shared images online, professional observatories released refined data, and simulations ran continuously to predict its closest approach. Each observation sharpened understanding, but also revealed more unpredictability. The comet, it seemed, had been designed to test observation, patience, and humility. Its threat was not a certainty, yet ignoring it was not an option. By now, the comet had moved from theoretical curiosity to an object of active scrutiny. Its late arrival, its unpredictable behavior, and its proximity to Earth created a tension that was both scientific and human. Scientists discussed probabilities, paths, and contingencies. Public interest lagged behind, focused on more glamorous celestial phenomena. Yet, in the quiet offices, observatories, and digital networks, the comet had become a focal point, an emblem of the unseen, a reminder that even small objects can demand our attention, humility, and respect. And as the narrative unfolds, it becomes clear that this comet's threat is about more than just physical proximity. It is about awareness, preparation, and the capacity to notice what others do not. The late arrival, the erratic flares, the small size. All these factors combine to create a lesson in vigilance. The universe does not accommodate schedules or headlines. It tests our systems, our perception, and our readiness. Tonight, as we continue this journey, we will trace the comet's path, analyze its behavior, and explore the implications of its unpredictable nature. The threat it represents is both real and symbolic. A reminder that the cosmos moves independently, and that our survival depends not only on technology, but on attentiveness, patience, and respect for the subtle signals of the universe. In the chapters to come, we will see how this threat evolves, how scientists respond, and how humanity confronts an object arriving quietly yet insistently at the edge of our awareness. In the end, the comet's threat is not about panic. It is about perspective. It teaches humility, observation, and vigilance. And above all, it reminds us that in a universe filled with spectacle, sometimes the quietest arrivals carry the loudest lessons. The night sky is vast, indifferent, and filled with secrets. For most of humanity, these secrets pass unnoticed, mere points of light in an infinite canvas. But for those tasked with understanding the cosmos, every flicker, flare, and motion is a potential clue, a piece of the puzzle that can explain the past, predict the future, or in rare cases, warn of a threat. With the late arriving comet now on the radar, the chase for data became urgent. Observatories across the globe shifted their focus, telescopes aligned, sensors calibrated, and eyes strained to capture every photon emitted from a small, unpredictable visitor. At the heart of this effort were the astronomers, both professional and amateur, whose lives had become a blend of patience and anticipation. Each measurement was a note in a symphony of observation. Every image, spectrum, and light curve contributed to a growing understanding of the comet's behavior. The challenge was not merely capturing data, but interpreting it correctly. Flares could indicate outgassing, fragmentation, or a previously unseen surface composition. A slight wobble in trajectory might be a gravitational nudge or a sign of rotational instability. Each detail mattered, and misinterpretation could lead to critical errors in predicting its approach to Earth. Data collection was relentless. Observatories in Chile, Hawaii, and the Canary Islands worked in coordination, covering the comet from multiple angles. Automated telescopes scanned the sky for motion and brightness changes. Amateur astronomers with backyard equipment contributed real-time images that were cross-referenced with professional observations. For the first time, a network of eyes spanning continents worked together to monitor an object that had arrived unannounced and late. The collaboration was quiet, understated, yet powerful. a testament to the modern age of shared knowledge and human curiosity. The chase for data also revealed the limitations of our systems. Even the most sophisticated telescopes cannot cover the entire sky simultaneously, and even advanced tracking algorithms rely on repeated observations to refine predictions. The comet's unpredictable flares complicated the process, as each surge of brightness required recalibration of its trajectory. Scientists often worked in shifts, comparing observations, checking logs, and updating models. Each update changed the story slightly, as new measurements replaced assumptions, and predictions became increasingly precise, but never perfectly certain. While the scientific teams focused on data, the public remained largely unaware of the magnitude of the effort. Headlines still favored 3i Atlas, the interstellar celebrity that dominated space news. But in quiet offices, under dim lights and amid stacks of charts and computers, the real work was happening. It was meticulous, iterative, and exhausting, yet profoundly necessary. Every new observation was a step toward understanding, a small victory against uncertainty. The comet's flares, unpredictable and dramatic, became the most challenging aspect of the chase. Each flare represented a sudden release of gas and dust from its surface, effectively acting like a tiny rocket engine. This could alter the comet's velocity and direction in ways that standard calculations could not fully anticipate. Scientists quickly adapted, creating real-time models that could incorporate new data on the fly. Every flare was a puzzle, and every puzzle piece moved in three-dimensional space at tens of kilometers per second. The stakes were high, but the pursuit was a dance of precision and patience. Meanwhile, software engineers and data analysts worked behind the scenes, creating pipelines that could process terabytes of observational data. Automated scripts flagged unusual patterns, cross-referenced multiple sources, and predicted possible trajectories. Humans then reviewed these outputs, verifying the predictions and adjusting models based on intuition and experience. It was a synergy between machine efficiency and human judgment, a collaboration that underscored the complexity of tracking a small, unpredictable object in a vast solar system. The chase was not without drama. A sudden brightening would trigger an alert, mobilizing observatories that were hundreds or even thousands of miles apart. Scientists would coordinate across time zones, sending emails, video calls, and instant messages, comparing notes and confirming measurements. Each alert was a moment of intense focus, a reminder that the universe does not pause for convenience and that vigilance can never truly rest. As the days progressed, patterns began to emerge. The comet's trajectory showed slight deviations caused by solar radiation, sublimation jets, and rotational dynamics. Its flares provided clues about its composition, suggesting pockets of volatile ices and perhaps unusual minerals. With each new piece of data, scientists refined predictions for its closest approach, narrowing uncertainty, but never eliminating it entirely. The chase was ongoing, an iterative cycle of observation, analysis, and adaptation. The process also illuminated the human side of discovery, the thrill of catching a new flare, the satisfaction of confirming an unusual trajectory, the camaraderie of sharing images and data across continents. All these elements reminded those involved why they watched the sky with such dedication. It is not fame or recognition that drives these individuals, but curiosity, wonder, and the deep-seated need to understand the universe that cradles our tiny planet. By now, the comet had transformed from an abstract risk to a tangible object of fascination. Its presence forced a reconsideration of assumptions, challenged observational infrastructure, and highlighted the limitations of human and technological preparedness. And yet, despite its unpredictability, the object was teaching something invaluable, that vigilance, patience, and collaboration are the ultimate tools in navigating a universe full of surprises. Finally, the chase for data was about more than predicting a path or assessing risk. It was about perspective, Each measurement reinforced how small humanity is in the grand scheme of space, how fleeting our attention can be, and how vital it is to remain observant, curious, and humble. The comet's late arrival and erratic behavior served as both challenge and lesson, a reminder that the cosmos operates on its own terms, indifferent to human expectation, yet rich with opportunities for understanding. As this chapter closes, the data collected becomes a foundation for what comes next: models, simulations, and eventually preparation. Each flare, each observation, each cross-check is a thread in the larger tapestry of knowledge. The chase is relentless, precise, and sometimes exhausting, but it is the only way to uncover the truth behind an object that arrived quietly, unpredictably, and insistently at the edge of human awareness. The universe has presented a puzzle, and humanity, through patience, vigilance, and collaboration, is now beginning to solve it. The comet is no longer just an accidental discovery. It is a test, a lesson, and a story of observation that binds science, curiosity, and human resilience together. And so the chase continues, as we follow every flare, every trajectory, and every subtle clue that the cosmos provides. Time moves differently when a cosmic visitor draws near. For the comet quietly slipping into our solar system, the countdown to its closest approach transformed abstract measurements into tangible tension. Every observation now carried weight. Every calculation mattered. It was no longer just a distant object on a telescope screen. It was a presence, approaching a point in space where physics, probability, and human attention converged. As the comet entered the final stretch of its journey toward Earth, astronomers began issuing more precise forecasts. Using a combination of radar, optical imaging, and trajectory modeling, teams calculated its path with increasing accuracy. The comet's distance, previously uncertain by hundreds of thousands of kilometers, became clearer with each passing hour. Scientists now knew not only how close it would come, but also the angle of its approach, the speed at which it traveled, and the orientation of its nucleus as it spun through space. Observers around the world tuned their instruments with heightened intensity. Telescopes in the southern hemisphere captured a brilliant, elongated streak in the sky, while those in the north recorded subtle shifts in its brightness. Amateur astronomers, too, shared their images online, providing a constant flow of data that helped refine models. It was a rare moment in human observation. The collaboration of professionals and enthusiasts, united by the urgency of a late-arriving object and the need to understand its behavior before it reached its closest point to our planet. The comet's behavior remained unpredictable, and that unpredictability heightened the sense of immediacy. Flares continued to erupt sporadically, sending plumes of gas and dust into the surrounding space. Each flare acted like a tiny thruster, subtly nudging the comet along its trajectory. These small forces, when compounded over millions of kilometers of travel, could change its position enough to make previously calculated safe distances less certain. Every flare was a reminder of nature's immense power and humanity's fragile grasp on knowledge. Scientists worked tirelessly to simulate these dynamic factors. Using supercomputers and complex algorithms, they modeled countless scenarios, testing how solar radiation, gravitational interactions, and the comet's rotational dynamics would affect its flight. Each simulation generated new insights, but also new questions. Could a sudden outburst cause it to fragment? Could the trajectory shift closer to Earth than anticipated? While the likelihood of collision remained low, the very uncertainty demanded attention. For the public, awareness remained limited. Headlines continued to feature the more sensational interstellar spectacle of 3I Atlas. Yet the comet's approach, although quieter, was no less significant. In scientific circles, it had become the object of intense focus. Professionals discussed it in emails, forums, and video conferences, sharing data and debating interpretations. Each measurement, no matter how small, contributed to a growing understanding, a mosaic of knowledge built in real time. The closest approach also provided opportunities for discovery. As the comet moved nearer, astronomers could observe features previously impossible to resolve. Small jets, the texture of the nucleus, and variations in composition became visible, revealing the comet's secrets layer by layer. These observations were not just important for tracking trajectory, they offered insight into the formation and evolution of small bodies in our solar system, illuminating processes that have remained hidden for millions of years. Meanwhile, the psychological tension among observers was palpable. Unlike distant or routine observations, the comet's proximity created a sense of immediacy. Every flare, every shift in position felt magnified. Teams worked in shifts, monitoring feeds from multiple observatories, cross-referencing data, and updating models continuously. The approach was a live test of human endurance, scientific precision, and the ability to respond rapidly to evolving information. Despite the tension, there was also beauty in the comet's approach. Against the canvas of the night sky, it became a moving sculpture of light and shadow. Its flares illuminated streams of dust, its tail stretched toward the sun, and its presence reminded humanity of the vastness and majesty of the cosmos. Observation became a blend of science and wonder, with each new image provoking both analytical thought and emotional awe. As the closest approach drew nearer, safety calculations became the priority. Planetary defense experts considered hypothetical impacts, modeling potential atmospheric entry, fragmentation, and energy release. While the comet was unlikely to collide with Earth, understanding these scenarios was critical. Even a near miss could provide data on how small, unpredictable objects behave in proximity to our planet, information vital for preparing for future encounters. The comet's approach also emphasized the importance of early detection. Its late discovery had compressed the timeline for analysis and decision-making. Scientists reflected on the gaps revealed by this event. Areas of the sky poorly monitored, thresholds for automated alerts, and the limitations of existing surveillance infrastructure. The experience became both a warning and a learning opportunity, highlighting how vigilance and preparation can mitigate uncertainty in a universe governed by its own rules. In the final hours before closest approach, observation intensified. Every telescope, sensor, and imaging tool focused on the comet. The public might have remained largely unaware, but the scientific community was alive with anticipation. Real-time feeds allowed continuous monitoring of flares and position, while simulation updates refined predictions to remarkable precision. It was a moment when patience, preparation, and collaboration converged, revealing the comet's journey in vivid detail. And then, the closest approach occurred. In human terms, it lasted minutes. In cosmic terms, it was a fleeting moment of alignment, a point when distance, velocity, and observation intersected perfectly. The comet passed safely, just as simulations predicted, leaving behind a trail of dust and a wealth of data. Scientists recorded, celebrated, and analyzed every aspect, while reflecting on the lessons learned from a visitor that had arrived late, behaved unpredictably, and yet, ultimately, remained harmless. The story of the closest approach is more than an event. It is a narrative about observation, curiosity, and preparedness. It underscores the delicate balance between chance and planning, between the unpredictable cosmos and humanity's efforts to understand it. The comet, small and almost invisible, arrived quietly, reminded us of our limitations, and left with a legacy of knowledge and reflection. As the night sky resumed its silent vigil, the comet moved onward, continuing its journey around the sun. Humanity had watched, recorded, and learned. And as we turn to the next chapter, we will explore how these observations inform our understanding of cosmic threats, planetary defense, and the very nature of vigilance in a universe full of surprises. The comet had passed. In the grand clockwork of the solar system, it was merely a tiny speck continuing its orbit around the sun. Yet for those who had tracked it so meticulously, every second of its passage carried profound significance. The closest approach was over, but the story was far from complete. Now came the period of reflection, analysis, and interpretation. a time when data transformed into understanding, and uncertainty yielded lessons that could prepare humanity for the future. As the initial excitement faded, observatories worldwide began compiling the torrents of information collected during the comet's approach. Images from different continents, spectra from multiple instruments, and the meticulous logs of flares, rotations, and trajectory shifts coalesced into a vast archive. For astronomers, this was more than a record. It was a story written in light, motion, and physics, one that demanded careful reading. Every data point represented a decision, a prediction, or a recalibration, and the patterns that emerged revealed both the elegance and the unpredictability of small bodies in space. The first analysis focused on trajectory validation. Scientists compared pre-approach predictions with the actual path of the comet. The early uncertainty, driven by its late detection and erratic flaring, had been reduced to a margin of mere kilometers. Each refinement was a triumph of observational science and computational modeling, highlighting the capacity of human ingenuity to track even the most elusive visitors in the cosmos. But beyond validation, these observations raised new questions. How do the comet's flares alter its trajectory in subtle ways? Could similar behavior in future objects catch humanity off guard? The answers, researchers realized, would take months of study. The composition of the comet became a focal point. Analysis of the light reflected from its surface during flares provided clues about volatile ices, minerals, and potential fragments. Scientists noted areas of unusual brightness, suggesting pockets of material that were actively sublimating or breaking apart. Such observations were not only important for predicting motion, but also offered insight into the formation of the solar system. Each comet carries within it a frozen record of billions of years of cosmic history, and this small visitor had revealed details previously unseen. Fragments of ancient ice and dust that told stories older than human civilization. Planetary defense experts, meanwhile, turned their attention to lessons learned. The compressed timeline between discovery and closest approach highlighted vulnerabilities in monitoring networks. While this comet posed no immediate danger, its late arrival exposed gaps in coverage, thresholds for automated alerts, and response protocols. These insights prompted immediate action, refining detection algorithms, coordinating global observation schedules, and re-examining scenarios for rapid response. In other words, while the comet had passed safely, its presence catalyzed preparation for the future. The human factor in the aftermath was equally significant. Observers reflected on the emotional intensity of the previous days. There had been tension, excitement, and the quiet thrill of discovery. Collaboration had flourished, both among professionals and amateurs. Shared images, real-time discussions, and coordinated observations created a sense of unity. For many, the comet's passage was a reminder of why we look to the sky, not only to anticipate danger, but to marvel at the elegance and complexity of a universe that moves on its own clock. Public engagement, however, remained a challenge. While the scientific community had been abuzz with data, few outside the field understood the significance of what had occurred. The comet's quiet, almost unnoticed approach contrasted sharply with the headlines around 3I Atlas, which dominated attention with spectacle and interstellar intrigue. This discrepancy highlighted a persistent truth. Humans are drawn to drama and novelty, sometimes at the expense of recognizing subtle but potentially consequential phenomena. The comet's story, though quieter, was a vital lesson in attention and awareness. Next came the synthesis phase, connecting data points across time, instruments, and observations. Researchers mapped flares to rotational models, cross-referenced brightness variations with sublimation patterns, and simulated potential fragment paths. The result was a rich, multidimensional portrait of the comet's behavior, a narrative of movement, composition, and cosmic forces at play. Each piece of the puzzle revealed more about the object itself, and about how humanity can predict, understand, and respond to similar events in the future. In addition, the comet's passage offered broader philosophical insights. It reminded humanity that even when events pass without catastrophe, there is value in vigilance, patience, and careful observation. The comet had arrived quietly, unpredictably, and without spectacle, yet it had captured the full attention of those willing to watch, analyze, and learn. Its story was a metaphor for our relationship with the universe, subtle, often unnoticed, yet rich with lessons for those prepared to see. Lessons from the aftermath also included the importance of international collaboration. Observatories in multiple countries, amateur and professional alike, had coordinated efforts to track the comet. This cooperation underscored the value of shared knowledge, open data, and rapid communication. In a global system, threats, or opportunities for discovery, are rarely confined to a single location. Science thrives when boundaries are crossed, when eyes are combined, and when insights are shared freely. Finally, the comet's passage reinforced humility. Despite advanced technology, predictive models, and extensive monitoring networks, there remained uncertainty. Nature, in its infinite complexity, cannot always be fully anticipated. The comet, small and late to our notice, challenged assumptions, revealed vulnerabilities, and yet also demonstrated the power of human observation, collaboration, and adaptability. It was a cosmic test, passed safely, but leaving profound reminders of the need for continuous vigilance. As the comet receded into the depths of space, leaving a trail of dust and knowledge, humanity's gaze returned to the broader sky. The immediate tension had passed, yet the lessons endured. Observation, preparation, collaboration, and humility. These were the legacies of the comet's approach. Its journey had been brief in cosmic terms, but long in human awareness, stretching across hours, days, and countless measurements that connected people and instruments in pursuit of understanding. The aftermath, therefore, was not just about data, but about perspective. Scientists reflected on the balance between spectacle and subtlety, urgency and patience, certainty and curiosity. The comet had offered both a challenge and an opportunity, and the analysis revealed not only how the cosmos operates, but also how humanity responds. In the chapters to come, we will explore how these insights inform our readiness for future encounters, the strategies developed for early warning, and the ongoing quest to reconcile our curiosity with the unpredictable rhythms of space. In the end, the story of the comet's closest approach and subsequent analysis is a testament to the quiet heroism of observation, the relentless pursuit of knowledge, and the enduring wonder of the cosmos. It is a reminder that vigilance is both scientific and philosophical, that lessons come from observation as much as from experience, and that the universe continues its course, indifferent but infinitely instructive, ready to reveal its secrets to those prepared to watch and learn. As the comet receded into the vastness of space, leaving Earth unscathed, humanity had much to digest. The close approach had been a wake-up call, a reminder that even small, late-discovered objects could test the limits of our planetary defense. From mission control rooms to amateur astronomers' backyards, the discussions were not just about the comet itself, but about the frameworks, technologies, and protocols that govern Earth's preparedness for cosmic threats. Above the Earth, the International Space Station, ISS, sailed silently across the night sky, its solar panels glinting in the sun's fading light. For billions of people below, it was a faint, beautiful streak of light, a symbol of human ingenuity and vigilance. For scientists and defense strategists, the ISS represented a critical vantage point. Orbiting above most of Earth's atmosphere, it provided unique observational capabilities, a platform for experiments, and a reminder of the interconnectedness of space and planetary defense. Every sensor, every camera, every instrument aboard the ISS contributed to humanity's understanding of near-Earth objects. even if most people never realized it. The comet had underscored vulnerabilities in our detection systems. It had arrived late, flaring unpredictably, and passing close enough to force real-time recalculation of risks. Planetary defense experts studied these gaps, noting that surveillance coverage was uneven, automated alert thresholds needed refinement, and communication between global networks could be improved. Each of these lessons was critical because the cosmos does not operate on human schedules, and even small objects can have outsized consequences if overlooked. One of the first lessons was the importance of redundancy. Just as the ISS is designed with multiple layers of systems to withstand failures, planetary defense relies on overlapping networks of telescopes, radar arrays, and satellites. No single instrument can cover the sky completely, and no single alert system is infallible. By ensuring redundancy, scientists can cross-check observations, verify anomalies, and reduce the chance that a potentially hazardous object slips by unnoticed. Another lesson was the value of international collaboration. During the comet's approach, data flowed from observatories in South America, North America, Europe, and Asia. Amateur astronomers shared critical images, while professional teams processed and analyzed the data. This global effort highlighted that threats from space are not constrained by borders. Earth's defense depends on coordinated observation, rapid communication, and shared responsibility. In this sense, the comet's near miss became a practical rehearsal for worldwide collaboration in response to future threats. The ISS, orbiting roughly 420 kilometers above the planet, also reminded researchers of the advantage of orbital platforms. Instruments aboard the station can monitor Earth, the Moon, and near-Earth space in ways impossible from the surface. Future planetary defense strategies may increasingly leverage orbiting assets to provide early warning, high-resolution imaging, and even experimental mitigation technologies. The ISS, while primarily a research laboratory, demonstrated the potential of space-based assets in safeguarding Earth. The unpredictable flares of the comet offered lessons in dynamic threat assessment. Unlike large predictable objects, small comets and asteroids can behave erratically. Sublimation jets, rotational wobble, and fragmentation can subtly but significantly alter trajectories. Scientists realized that planetary defense is not just about cataloging objects. It is about constantly updating models, running simulations, and maintaining flexibility in decision-making. The cosmos rarely provides simple, linear problems. It offers complex systems that demand vigilance, adaptation, and expertise. Communication and public awareness were also key takeaways. While the comet had been extensively observed, most of the public remained focused on the interstellar spectacle of 3I Atlas. This gap highlighted the need to convey critical information effectively without causing panic but ensuring informed engagement. Planetary defense is as much about education as it is about detection, making the invisible risks tangible, comprehensible, and actionable for policymakers and the public alike. Data sharing frameworks emerged as another lesson. During the comet's passage, data arrived from multiple sources in diverse formats. Analysts had to integrate images, light curves, and radar measurements into a cohesive understanding. The process highlighted the need for standardized protocols, automated data pipelines, and cloud-based collaboration tools to ensure that information is accessible and usable in real time. The ISS overhead was more than symbolic. It was practical. Scientists aboard the station could monitor meteor showers, track orbital debris, and even test early warning instruments that might one day detect incoming objects before they reached Earth. Lessons learned from the comet would inform experiments on the ISS, bridging observational astronomy with practical defense measures. In this way, the station became both observer and laboratory, a sentinel orbiting silently above a world that depends on its vigilance. The comet also emphasized the importance of simulations and scenario planning. Planetary defense is not reactive, it is predictive. By modeling countless trajectories, including worst-case possibilities, scientists can anticipate risks and develop mitigation strategies. Simulations allow agencies to test response plans, evaluate resource allocation, and refine communication strategies. The late-discovered comet had been an unexpected stress test, revealing strengths and weaknesses in both technology and human coordination. Finally, the episode reinforced a philosophical truth. The universe is indifferent, but humanity's response need not be. Vigilance, preparation, and collaboration turn cosmic indifference into actionable knowledge. The ISS flying overhead, the telescopes scanning distant skies, and the countless observers recording, calculating, and theorizing are evidence that humans, though small and fragile, can engage meaningfully with a universe that often seems indifferent. As the aftermath of the comet's closest approach settled, planetary defense became not a theoretical exercise but a tangible mission. Lessons learned would shape policy, technology, and education. The ISS would continue its silent patrol, orbiting as both witness and participant in humanity's preparation. Global networks would refine detection, simulation, and communication, and future small comets would be met with greater readiness. The story of this comet, while quiet in public attention, became a profound lesson in awareness, preparedness, and collaboration. Earth had been lucky this time, but the universe rarely waits for notice. And as the ISS traced its elegant arc across the night sky, reflecting sunlight like a distant guardian, humanity was reminded of its place in the cosmos. Small, curious, and ever vigilant. The comet's visit had ended, but the work of observation, analysis, and defense was just beginning. Humanity had chased data, survived the close approach, and now stood ready to learn, adapt, and prepare for the next visitor from the infinite darkness above. The comet had passed, the closest approach safely behind humanity, and yet the story was far from over. While scientists quietly celebrated the triumph of prediction, observation, and analysis, the public reaction painted an entirely different picture, a kaleidoscope of curiosity, confusion, and fascination. From social media threads to news headlines, people everywhere were processing what they had glimpsed or imagined in the skies. This chapter of the story is not about celestial mechanics or flares. It is about the human narrative, the way events in the cosmos ripple down to influence perception, discussion, and understanding here on Earth. The headlines told one story, often sensationalized. A monster approached Earth, screamed banner text on several outlets, accompanied by dramatic graphics of comets hurtling toward a planet that gleamed in the void. The interstellar interloper 3I Atlas still dominated many conversations, but this smaller, unpredictable comet, the one that had slipped by almost unnoticed, became the quiet undercurrent of concern for those paying attention. Media outlets faced a tension between what was scientifically important and what would draw clicks, a balance between responsibility and spectacle that was rarely perfect. Social media, however, became the arena where engagement exploded. On platforms like Twitter, Reddit, and YouTube comment sections, users debated, speculated, and shared images of the comet captured from backyard telescopes. Amateur astronomers proudly posted their tracking photos, showing streaks of light that few eyes could see in real time. Each photo and video became a piece of collective storytelling, with users interpreting events, asking questions, and theorizing about potential impacts. Memes even emerged, blending humor with awe, transforming the comet into a symbol that was simultaneously feared and adored. The reaction also revealed a fascinating aspect of human psychology: the gap between awareness and understanding. Many viewers who had seen headlines were captivated by the term monster, without fully appreciating the nuances of orbital mechanics or the rarity of a near-miss event. This gap created fertile ground for curiosity, education, and, at times, misinformation. Some posts suggested doomsday scenarios, exaggerated the size or speed of the comet, or misattributed its behavior to alien technology, echoing the sensationalism that often accompanies cosmic events in the public imagination. Journalists and communicators faced a delicate challenge, translating complex, precise scientific data into narratives accessible to the general public without causing unnecessary panic. Press releases highlighted that the comet had been thoroughly tracked and posed no real threat, yet the drama of its flaring, late discovery, and sudden appearance made it difficult to downplay. Headlines competed for attention, and the narrative often tilted towards suspense. However, those outlets that included context, visualizations, and expert commentary succeeded in providing viewers with a balanced understanding, blending awe with reassurance. Public forums became spaces of debate and education. Users asked questions such as, why was the comet discovered so late? Could a similar object pose a real threat in the future? How do scientists predict trajectories with such precision? Professionals and enthusiasts alike engaged, sharing insights, correcting misconceptions, and providing mini-lectures in plain, digestible language. The conversation shifted from fear to curiosity, and the comet became a catalyst for learning, exploration, and engagement with the night sky. Interestingly, the comet's passage also illuminated how humans respond emotionally to cosmic events. There was awe in the face of its trajectory, tension in the uncertainty of its flaring behavior, and relief once it had passed. This emotional roller coaster mirrored the stages of a narrative arc: anticipation, climax, and resolution. It was a reminder that humans are storytellers at heart, interpreting natural phenomena as dramas in which we play the role of both observer and audience. Media coverage also highlighted the contrast between spectacle and subtlety. While 3i Atlas captured attention with its interstellar origin and mysterious behavior, the smaller comet required a different kind of appreciation. It demanded attention to detail, patience, and trust in scientific expertise. Its understated approach demonstrated that not all significant events arrive with fireworks. Some teach lessons quietly, yet profoundly, in the way they test systems, reveal gaps, and reward observation. Educational institutions and science communicators seized the moment. Live streams, online lectures, and news segments explained the comet's composition, orbital path, and the principles behind planetary defense. Children and adults alike were introduced to concepts such as sublimation, trajectory modeling, and flare dynamics. By translating the event into stories, visuals, and analogies, educators fostered curiosity and resilience, a generation learning that the universe is vast, unpredictable, and fascinating, yet navigable through knowledge. The ISS overhead served as a powerful visual anchor in media coverage. Animated graphics showed the space station gliding past Earth, while the comet streaked below, symbolizing humanity's vigilance and technological achievement. It reminded viewers that while cosmic objects are vast and indifferent, humans have built instruments, networks, and strategies to observe, analyze, and respond. The orbiting ISS became a symbol of reassurance, signaling that preparation, science, and global collaboration are tangible defenses in a universe that rarely waits for our attention. In the aftermath, discussions extended beyond immediate impacts to broader philosophical questions. What does the comet tell us about humanity's place in the cosmos? How can we balance curiosity with caution? The event became an invitation to reflect on preparedness, humility, and the awe-inspiring scale of space. News stories and social media threads alike pondered not just what might have happened, but what the comet teaches us about vigilance, knowledge, and collaboration. By the end of the week, a pattern emerged. Public reaction evolved from sensational fear to informed curiosity. People celebrated the success of observation, marveled at the close approach, and engaged with science more deeply than they might have otherwise. The comet had acted as a bridge, connecting professional knowledge with public imagination, and transforming a fleeting celestial event into a lasting narrative about observation, preparation, and understanding. Ultimately, The comet's story is inseparable from the human response. The media narrative, public curiosity, and emotional engagement all form a constellation of meaning that extends beyond the object itself. It illustrates how cosmic events, though governed by physics and probability, ripple through human society in unpredictable ways, shaping learning, dialogue, and appreciation for the universe. As the ISS glided silently above, reflecting sunlight like a guardian of knowledge, the story of the comet became a testament not just to science, but to human attention, resilience, and the enduring capacity for wonder. The chapter closes with a profound realization. The cosmos will continue its dance, sending visitors large and small, spectacular and subtle. How humanity observes, communicates, and reacts is what transforms these events from mere data points into shared experience, lessons, and stories that endure. As the comet's brief visit faded into memory, scientists across the globe began the meticulous task of extracting knowledge from its fleeting passage. What had been a tense, awe-filled spectacle now became a rich tapestry of data, observation, and revelation. Every flare, trajectory shift, and spectral signature became a window into the behavior of small celestial bodies, and by extension, into the subtle laws of the cosmos. For researchers, the comet's passage was less about fear and more about enlightenment. The universe had whispered a lesson, and those who listened carefully would understand. The first insights emerged from the orbital anomalies. The comet's flaring, unpredictable bursts of brightness revealed that it was not a simple, inert chunk of ice and dust. Jets of sublimating gases, interacting with its rotation and uneven surface, had subtly altered its path. Tracking these deviations required constant recalibration of predictive models. The surprise? Even small, previously unnoticed comets could exhibit behaviors capable of challenging the precision of our detection algorithms. Scientists realized that the cosmos is more dynamic, more fluid, and more complex than their models often assumed. Spectroscopic analysis provided another layer of revelation. Observatories focused on the light reflected by the comet uncovered unexpected chemical signatures. While standard water ice and silicate minerals were present, unusual ratios of carbon compounds hinted at a history distinct from most near-Earth comets. These chemical anomalies prompted questions about the comet's origin. Was it a fragment of a long-lost distant planetary system, or simply an oddball formed in the outskirts of our own? Each discovery reminded researchers that even familiar-looking celestial objects could carry surprises written in their composition, like ancient diaries waiting to be deciphered. Amateur astronomers played a surprisingly significant role. Observers with backyard telescopes captured flares and fragmentation events that professional instruments had barely detected. Their photos, time-stamped and geotagged, contributed to a distributed network of observational data, demonstrating the power of citizen science. It was a reminder that in the age of global connectivity, science is not confined to labs and observatories. Anyone with curiosity, diligence, and access to technology can become a contributor to knowledge. Perhaps most fascinating was the comet's fragmentation behavior. Small pieces of debris were shed during flares, creating transient mini-meteoroid streams. These fragments illuminated the physics of material stress, sublimation, and rotation in microgravity, processes that are otherwise challenging to observe. The behavior raised practical questions. How do we monitor fragments that are too small to trigger automated detection systems? Could similar fragments pose risks to satellites, the ISS, or even Earth's upper atmosphere? Each answer sparked new questions, a recursive loop of discovery and planning. Researchers also turned to the comet's unexpected brightness fluctuations. While initially alarming to the public, these fluctuations revealed the mechanics of light reflection, surface irregularities, and the influence of rotational orientation. By analyzing how light varied over time, scientists could infer the comet's shape, rotation period, and even estimate surface topography. A remarkable achievement from a small, distant visitor. The surprise was how much information could be gleaned from careful observation, patience, and analytical rigor. The ISS, orbiting silently above, became a subtle yet essential witness. Instruments aboard the station, including cameras and spectrometers, had observed the comet from unique angles inaccessible from Earth's surface. Their data provided cross-validation of ground-based observations, confirming flares, rotation rates, and fragmentation events. The ISS illustrated that orbital platforms are not only scientific laboratories, but also sentinels, enhancing humanity's ability to detect, measure, and understand the behavior of near-Earth objects. Global cooperation emerged as another key insight. Data flowed from multiple observatories, institutions, and even private networks, highlighting the importance of real-time, collaborative science. Different wavelengths, instruments, and perspectives converged into a single, coherent understanding of the comet's nature. The event served as a rehearsal for future, more urgent encounters, demonstrating how distributed observation networks can generate comprehensive insights even under tight timelines. Unexpected discoveries extended to planetary defense strategies. While the comet posed no imminent threat, its unpredictable flares and late detection revealed weaknesses in early warning systems. Analysts realized that their tracking thresholds, alert criteria, and coordination protocols needed refinement. Lessons learned would inform future detection algorithms, simulation models, and operational readiness. In other words, the comet's surprise behaviors became a catalyst for practical, preventative innovation. Perhaps the most profound scientific insight was philosophical. The universe remains unpredictable, even in ways we believe we understand. Models, simulations, and previous experience can only take us so far. Nature, in its complexity, resists complete certainty, yet through observation, collaboration, and analytical rigor, humans can reduce uncertainty, anticipate risk, and extract knowledge from fleeting moments. The comet, small and late discovered, had provided a window not just into its own nature, but into the broader challenge of understanding a universe that operates on scales, forces, and times beyond everyday experience. Finally, the comet's passage emphasized the value of continuous vigilance. Observing the unexpected is not a luxury, it is a necessity. Small comets, minor fragments, and subtle flaring events may hold keys to predicting hazards, understanding cosmic chemistry, and preparing for the future. Each observation, each data point, becomes part of a growing archive of knowledge that strengthens humanity's resilience. The ISS, orbiting above as both observer and laboratory, reminded the world that science and preparedness are inseparable. The cosmos may not wait, but humans can learn, adapt, and respond. By the end of the analysis, the comet's story had transformed. It was no longer a passing curiosity or a fleeting scare. It became a rich chapter in the ongoing narrative of humanity's engagement with the cosmos. The unexpected flares, fragmentation, and chemical surprises illuminated both the object itself and the systems humanity relies on to understand the skies. Insights gleaned from its behavior informed not just theoretical models but practical strategies, educational outreach, and global collaboration. The ISS glided across the night sky as observers below reflected on the lessons learned. The comet's surprises, small and subtle though they were, became a testament to human curiosity, diligence, and ingenuity. Science had turned uncertainty into understanding, awe into knowledge, and a fleeting visitor into a permanent lesson. In this cosmic dance, the surprises of one small comet ripple outward, shaping how humanity perceives, prepares, and thrives amidst the vast, unpredictable universe. The comet had passed, yet its visit was far from over in the eyes of the scientific community. What began as an isolated observation quickly transformed into a massive, coordinated global response, a testament to how humanity can unite when facing the unpredictable vastness of space. Across continents, observatories, satellites, amateur astronomers, and orbital platforms like the ISS became part of an intricate network, each node contributing to a deeper understanding of the comet and, by extension, the universe itself. From the moment astronomers first detected the comet, alerts traveled faster than the object itself. Networks spanning North and South America, Europe, Asia, and Oceania shared real-time data, timestamps, and imaging. Scientists compared observations, reconciled discrepancies, and refined orbital models hour by hour. Unlike a solitary observation that might miss a subtle deviation, this global collaboration created a dynamic, living picture of the comet's behavior. It was as if the planet itself had collectively trained its gaze on the sky, each observer contributing to a human eye of unprecedented scale and acuity. The ISS played a crucial role in this response. Orbiting above atmospheric interference, it provided perspectives and measurements unavailable from the ground. Cameras captured detailed images of the comet's flares and fragmentation, while spectrometers analyzed the chemical composition of its ejected material. Data from the ISS cross-validated ground-based observations, improving predictive models and offering scientists the opportunity to test real-time analysis tools in a high-stakes environment. The station's position over multiple time zones allowed for near-continuous observation, ensuring no critical moment went undocumented. One of the key lessons from the event was the value of redundancy and layered observation systems. No single observatory or instrument could provide a complete picture alone. Radar systems, optical telescopes, infrared detectors, and radio arrays were all brought into the fold. Each system complemented the others, filling gaps and confirming anomalies. The result was a comprehensive understanding of the comet's trajectory, behavior, and potential impact, a synergy of technology and human diligence that exemplified modern planetary defense. International collaboration extended beyond instruments to include real-time communication and decision-making protocols. Agencies across nations held emergency coordination calls, sharing verified data and discussing potential threats. While the comet posed no immediate danger, these exercises allowed agencies to rehearse procedures that would be critical in future scenarios. Decisions regarding observation priority, resource allocation, and information dissemination were made collaboratively, ensuring that no single entity bore the burden alone. It was a rehearsal for planetary defense writ large, a live-action simulation triggered by reality itself. Amateur astronomers contributed in ways that were both unexpected and invaluable. Backyard telescopes around the globe captured light curves, streaks of debris, and subtle flares that escaped automated detection systems. Their observations were shared via online platforms, geotagged and time-stamped, providing additional layers of verification. The democratization of observation turned a small but motivated global community into an indispensable part of scientific vigilance. The comet demonstrated that in the age of connected observation, professional and amateur efforts are not separate but intertwined, creating a richer, more resilient network of knowledge. The media narrative intertwined with this coordinated response, shaping public understanding and engagement. News outlets highlighted the global effort, framing the comet not merely as a celestial curiosity, but as a demonstration of human collaboration and technological achievement. Visualizations showed satellites, telescopes, and the ISS tracking the comet in synchronized choreography, providing a tangible sense of scale and precision. For viewers, it became clear that scientific observation was not a solitary, abstract process, but a coordinated ballet of minds and machines spanning the planet. The comet also highlighted the importance of standardized protocols for data sharing. With hundreds of contributors worldwide, the challenge lay not just in gathering data, but in integrating it quickly and accurately. Shared file formats, automated processing scripts, and cloud-based platforms enabled scientists to analyze observations almost in real time. These frameworks ensured that even late-night or remote observations were immediately usable, reducing the risk of missing critical behavior. The experience underscored that coordination is not just about communication, it is about systems, standards, and trust. Simulation exercises ran in parallel with observation. As the comet's path became more accurately defined, predictive models tested hypothetical scenarios, examining what might have happened if fragments had altered course or if detection had been delayed further. These simulations informed emergency planning, refined impact probability estimates, and allowed agencies to practice rapid response procedures. They reinforced that observation alone is not sufficient. Coordinated planning is essential to translate knowledge into actionable readiness. A less visible but equally important aspect of the global response was educational engagement. Universities, museums, and science communicators leveraged the comet's passage to explain celestial mechanics, observational techniques, and planetary defense strategies to the public. Virtual workshops allowed students and enthusiasts to participate in data analysis, creating a sense of shared purpose and collective curiosity. In doing so, the comet became not just a threat assessment exercise, but a moment of inspiration, a demonstration that science is a participatory endeavor, open to anyone willing to look up and ask questions. The ISS's silent orbit overhead reminded the world of continuity and vigilance. While individual observations might end when night fell or instruments paused, the station continued its patrol, a constant sentinel capturing data, validating models, and providing a bridge between human curiosity and celestial mechanics. Its presence symbolized humanity's enduring commitment to understanding the universe, a steady, tireless observer watching as we learn, adapt, and collaborate. Ultimately, the comet became a case study in resilience, communication, and shared responsibility. It revealed how nations, agencies, and individuals can unite around a single objective: knowledge and preparedness. The global response did not just track a celestial object. It demonstrated the potential of coordinated human effort, technological ingenuity, and scientific discipline. By the time the comet receded beyond reach, humanity had gained far more than reassurance. It had gained experience, protocols, and a renewed understanding of what collaboration could achieve. The story of coordinated observation and global response was more than a technical account. It was a human narrative. It demonstrated how curiosity, diligence, and preparation can transform uncertainty into actionable insight. It showed that even fleeting, unpredictable events can catalyze innovation and reinforce the bonds of scientific community. And above it all, the ISS sailed across the sky, a silent witness to humanity's potential to act together in the face of cosmic indifference. As the chapter closes, it is clear that coordinated observation is not optional. It is essential. Every telescope, satellite, and citizen astronomer contributes to a mosaic of understanding. Every protocol, simulation, and communication channel strengthens resilience. And every orbiting station, silently patrolling the planet, reminds us that in a universe filled with surprises, humanity can still choose awareness, vigilance, and preparedness. The comet's fleeting visit had passed, but its lessons in collaboration, coordination, and cosmic humility would endure for generations to come. The comet's passage was over, but the work had only just begun. For scientists, engineers, and policymakers, the real task now was risk assessment, a meticulous, often invisible process that turns cosmic uncertainty into actionable knowledge. The unexpected appearance of this small but unpredictable comet revealed gaps in detection systems, timing, and response protocols. It was a reminder that while humanity can observe the heavens, it must also plan for the unplanned, prepare for the improbable, and anticipate the unpredictable. The first step in the process was trajectory analysis. Teams of orbital mechanics experts recalculated the comet's path, considering flares, fragments, and subtle gravitational influences from planets and asteroids. Using high-powered simulations and historical datasets, they measured the probability of future near misses or potential collisions. Every slight deviation became a critical variable. Even though the comet had passed safely, the exercise highlighted how small uncertainties can compound over time, emphasizing the need for vigilance and redundancy in observational systems. Fragmentation events presented a particularly thorny challenge. Tiny debris, undetectable in initial scans, could theoretically intersect Earth's orbit months or years later. Contingency planning involved modeling every fragment, their trajectories, and potential interactions with satellites, space stations, and atmospheric layers. This level of detailed analysis is rarely visible to the public, but forms the backbone of planetary defense. It illustrated how preparation is not just about reacting to the obvious, but predicting and mitigating invisible risks. Beyond physical trajectory, scientists considered the comet's chemical and physical composition. Unexpected compounds or volatile materials could, in a hypothetical scenario, create unpredictable flaring, break into hazardous fragments, or produce atmospheric effects. By understanding these properties, teams developed mitigation strategies, including early warning protocols, deflection simulations, and emergency response guidelines. Each piece of data transformed uncertainty into actionable foresight, demonstrating that knowledge itself is the most powerful tool in risk management. Simultaneously, international cooperation became central to contingency planning. Space agencies across the globe shared data, models, and best practices, ensuring no single nation bore the burden alone. Emergency communication protocols were tested, from rapid alert messaging to simulation drills for national and regional response teams. These rehearsals, though hypothetical, strengthened trust, verified capabilities, and improved the speed and accuracy of potential real-world interventions. The comet served as both a test case and a reminder that cosmic events respect no borders. The role of satellite infrastructure was also evaluated. Every orbiting telescope, Earth observation satellite, and communication relay was analyzed for vulnerability to debris or flaring material. Contingency planning included rerouting satellites, enhancing imaging schedules, and prioritizing data channels for critical observations. Even small disruptions in communication or observation could create blind spots, so preemptive adjustments were vital. This careful orchestration underscored the interconnectedness of space operations, planetary monitoring, and global security. On the ground, scientists developed tiered alert systems. These ranged from minor notifications to full-scale emergency preparedness protocols. By creating layers of response, authorities could escalate action proportionally to risk, avoiding unnecessary panic while ensuring readiness. This approach balanced public communication, safety, and scientific integrity, emphasizing that preparedness is as much about messaging as it is about monitoring. The comet also catalyzed the refinement of simulation and modeling software. Using real data from its flares, rotations, and fragmentation, scientists stress-tested predictive algorithms. Could these models accurately forecast deviations for months into the future? What if multiple small comets approach simultaneously? By challenging systems with edge-case scenarios, teams increased resilience, reliability, and confidence. The comet became both subject and teacher, revealing strengths and weaknesses alike. Importantly, human factors were considered in risk assessment, decision-making under uncertainty, the potential for miscommunication, and cognitive biases were all factored into contingency planning. Scientists and emergency managers recognize that even the best data can be undermined if human judgment falters. Training, cross-disciplinary drills, and clear communication protocols became integral components of preparation, ensuring that responses would be coordinated, rational, and timely. Public communication remained another crucial element. Lessons from the comet demonstrated that clear, calm, and factual messaging can prevent panic while promoting engagement and understanding. Contingency plans included press releases, visualizations, and Q&A frameworks designed to educate without sensationalizing. By building public trust in advance, authorities could rely on informed cooperation in any future scenario, transforming fear into constructive attention. The comet also spurred policy-level considerations. Governments evaluated funding for observation networks, early warning systems, and research initiatives. Policies were debated regarding resource allocation, international treaties, and coordination of emergency measures. The event highlighted that cosmic risks are not solely scientific problems. They are societal challenges requiring foresight, collaboration, and governance. The comet, tiny as it was, became a catalyst for policy reflection and structural planning. Finally, the chapter underscored a philosophical lesson. Preparation is empowerment. Risk assessment and contingency planning are acts of respect for the universe's unpredictability. They acknowledge that cosmic events will continue to occur, often beyond human control. But that knowledge, vigilance, and coordinated action can mitigate harm. The comet's late discovery, unpredictable flares, and subtle fragmentation reminded humanity that readiness is an ongoing journey, not a one-time effort. By the end of the exercise, the comet's passage had transformed into a blueprint for action. From orbital mechanics to human communication, from satellite coordination to global policy, every aspect of risk assessment and contingency planning was informed by the experience. The comet's presence, fleeting though it was, became a teacher, a warning, and a source of empowerment. It illustrated that while humans cannot control the cosmos, they can control their attention, preparation, and response, turning uncertainty into understanding and potential disaster into opportunity for growth. As night fell and the comet faded from view, the lessons lingered. The world had learned not only about celestial mechanics, but about its own systems of observation, response, and collaboration. The comet, silent and distant, had left a permanent imprint on human knowledge, strategy, and imagination. It became a testament to resilience, foresight, and the enduring human desire to anticipate, prepare, and thrive in a universe filled with both beauty and unpredictability. The comet's fleeting presence in Earth's sky was only the visible tip of an enormous iceberg. Beneath what the public saw, the images, the occasional news flashes, the curious headlines, lay a sprawling invisible web of technology and tools, a digital and mechanical ecosystem that allowed humanity to watch, track, and analyze a celestial visitor that appeared almost out of nowhere. Without these instruments, the comet would have passed unnoticed, a silent ghost in the void. But thanks to decades of innovation, collaboration, and persistent observation, it could be monitored in unprecedented detail. High above the planet, satellites and space telescopes formed the first line of observation. Unlike ground-based telescopes, these instruments were free from atmospheric distortion, capable of capturing light from the comet that never reached Earth's surface. Instruments like the Hubble Space Telescope and smaller survey satellites focused on capturing the comet's trajectory, composition, and flares. Infrared sensors, ultraviolet imagers, and spectrometers worked in concert, creating a multi-dimensional view. Each wavelength revealed a different story. Some highlighted dust clouds, others mapped out chemical composition, and still others monitored the thermal signature of volatile jets. It was as if the comet were being dissected by beams of light invisible to the human eye. Every photon carefully recorded. Down on Earth, optical telescopes and radio arrays formed the backbone of continuous monitoring. Massive observatories in Chile, Hawaii, and the Canary Islands combined high-precision mirrors, adaptive optics, and advanced detectors to track even the smallest deviations in the comet's path. Meanwhile, radio telescopes measured its interactions with solar radiation, providing critical data on its composition and potential for fragmentation. These instruments, often miles apart, were synchronized through atomic clocks and GPS, creating a global grid of precision. The comet was no longer a solitary object in the void. It was a node in a vast network of human technology. Amateur astronomers played an unexpectedly important role. Their backyard telescopes, modest compared to professional observatories, filled in gaps, captured sudden flares, and provided continuous coverage across time zones. Using shared platforms, these enthusiasts uploaded time-stamped observations, images, and light curves, which were then validated and incorporated into broader models. It was a democratization of cosmic surveillance. Anyone with a telescope, a camera, and an internet connection could contribute to planetary awareness. The real magic, however, lay in data integration systems. Observatories, satellites, and citizen scientists all produced vast amounts of raw data, terabytes of images, spectra, and telemetry every day. Specialized software processed these inputs, correcting for atmospheric distortion, parallax errors, and instrumental noise. Algorithms stitched together fragmented images, generated real-time orbital simulations, and predicted near-future positions with astonishing precision. These systems allowed scientists to see the comet not as a blur of light in the sky, but as a dynamic object with structure, behavior, and potential threats that could be forecasted. Central to this process was artificial intelligence and machine learning. Models were trained on decades of asteroid and comet observations, learning to detect subtle anomalies in movement, brightness, and composition. When the comet flared unpredictably, AI detected the pattern immediately, flagging it for human review. This allowed rapid adjustments to tracking schedules and observation priorities. AI also simulated thousands of potential trajectories, identifying those with even the smallest probability of Earth interaction. What once required weeks of manual calculation could now be done in hours, providing critical time for analysis and contingency planning. Communication networks tied it all together. Observatories around the world exchanged data via secure satellite links, high-speed fiber optic connections, and cloud-based platforms. Time-stamped observations, spectral readings, and predictive models were uploaded in near real time, enabling scientists to update calculations continuously. Slack channels, automated alerts, and live dashboards ensured that no critical moment went unnoticed. If one node failed, a telescope shutter stuck, a satellite signal lost, another could immediately fill the gap, ensuring continuity. Simulation played another critical role. Physics engines and orbital simulators recreated the comet's motion under various gravitational influences. The Sun, nearby planets, and even passing asteroids. These simulations accounted for outgassing events, the sudden eruptions of material from the comet's surface, and predicted how these jets could alter its path. Each simulation ran thousands of permutations, creating a probabilistic map of the comet's behavior. Scientists could test what-if scenarios. What if a fragment broke off? What if solar radiation caused an unexpected spin? Every potential contingency was modeled long before it could become reality. On the software front, visualization tools allowed both scientists and the public to see the comet in 3 dimensions. Dynamic renderings showed jets erupting, dust tails stretching across space, and predicted orbits superimposed on Earth's view. Animations highlighted relative speed, rotation, and interaction with solar winds, providing intuitive insight that raw numbers could never convey. These visualizations became key communication tools, helping policymakers, educators, and journalists understand complex data quickly and accurately. Even the ISS contributed to this technological web. Orbiting above atmospheric interference, it captured continuous observations and relayed real-time imaging to Earth-based systems. Instruments on board measured particle ejections, spectral emissions, and thermal output. By providing uninterrupted observation windows over multiple time zones, the ISS bridged gaps between terrestrial instruments and allowed scientists to verify data from multiple sources. Importantly, all of this technology operated under strict calibration, redundancy, and verification protocols. Sensors were constantly checked against reference standards. Software outputs were validated against independent calculations, and cross-observation comparisons were routine. The comet's unpredictable behavior demanded precision and accountability at every step. Every measurement, every image, every data packet was treated as sacred, a testament to the care humanity takes when facing the unknown. Lastly, the human element remained central. Operators, analysts, and engineers orchestrated this technological symphony, interpreting data, adjusting priorities, and making judgment calls where machines could not. Their expertise turned streams of numbers and images into actionable understanding. They monitored, corrected, and communicated, ensuring that even the smallest anomaly would not go unnoticed. Without their vigilance, the comet would have been just another dot in the sky. With it, it became a lesson in preparation, resilience, and the incredible power of coordinated observation. By the end of the comet's passage, it was clear that technology was not a tool alone. It was an extension of human curiosity, collaboration, and foresight. Satellites, telescopes, software, and AI had not only tracked a celestial visitor, but had demonstrated the potential of global, coordinated, high-tech vigilance. Every sensor, every algorithm, every observation contributed to a layered understanding that transformed uncertainty into insight. Humanity had reached out into space and, for a brief moment, caught a glimpse of the universe's secrets, all through the careful orchestration of tools, technology, and human dedication. Once the comet had been tracked and observed through every available lens, satellites, space telescopes, ground observatories, and even backyard instruments, the next stage began: data analysis and interpretation. This was the invisible heartbeat behind the visible spectacle, the intellectual machinery turning raw numbers, light signatures, and orbital positions into actionable knowledge. Without this step, the comet would remain a series of disconnected points in space. With it, humanity gained understanding, prediction, and ultimately foresight. The first task was data collation. Observatories around the world had collected terabytes of information: high-resolution images, spectrographic readings, thermal maps, and radio emissions. These datasets arrived in varying formats, resolutions, and timestamps. Before analysis could begin, they had to be standardized, corrected for observational inconsistencies, and synchronized across time zones. Every detail mattered. A minor timing discrepancy or a calibration error could lead to an inaccurate prediction of the comet's path. Teams of data engineers and astronomers worked tirelessly to clean, normalize, and integrate this sprawling universe of information into a coherent framework. Once the data was unified, scientists began orbital calculations and predictive modeling. Advanced algorithms incorporated gravitational influences from planets, solar radiation pressure, and even the effects of minor asteroids to determine the comet's trajectory. These models had to account for dynamic variables. The comet was not a rigid, inert body, but a volatile entity. Jets of gas erupted unpredictably, dust clouds shifted, and fragments occasionally detached. Each of these behaviors subtly altered its path. By running thousands of simulations, scientists created a probabilistic map of its movement, identifying potential close approaches and hypothetical intersections with Earth or satellites. Spectroscopic analysis played a central role. By splitting the comet's light into component wavelengths, astronomers discerned its chemical composition. Volatiles like water ice, carbon dioxide, and ammonia produced specific spectral fingerprints, while unexpected compounds hinted at unusual origins or history. This analysis not only revealed the comet's material makeup, but also provided insight into its potential behavior. Volatile-rich regions could lead to sudden outbursts, dust jets, or fragmentation, all of which had implications for risk assessment and observation planning. Thermal mapping provided another layer of understanding. Instruments sensitive to infrared emissions measured temperature variations across the comet's surface. These thermal anomalies often correlated with areas of volatile activity or structural weakness. By tracking these fluctuations over time, scientists could anticipate when and where eruptions or fragmentation events might occur. Thermal data, combined with spectral readings, gave a multi-dimensional picture of the comet, not merely as a moving point in space, but as a living, changing entity. At the same time, light curve analysis helped determine rotation, shape, and surface irregularities. By measuring the intensity and timing of reflected sunlight, astronomers inferred the comet's spin rate, axial tilt, and asymmetries in its shape. These subtle insights allowed for better predictions of how sunlight and solar wind would interact with the comet, affecting both its motion and the intensity of flaring events. Even the smallest variations could significantly alter trajectory predictions, reinforcing the importance of meticulous measurement and observation. Once raw data had been analyzed individually, the next step was cross-validation. Observations from satellites were compared with ground-based readings, amateur telescope reports, and predictive models. Discrepancies were not ignored. They were investigated and understood. Was a sudden spike in brightness an observational error, a fleeting flare, or a fragment breaking away? Each anomaly underwent scrutiny. This iterative process ensured that conclusions were robust, reliable, and not based on isolated observations or misinterpretations. Statistical modeling and probability assessments transformed observational data into decision-making tools. Scientists created likelihood estimates for various outcomes: the chance of Earth impact, even if infinitesimal, potential orbital shifts, and risks to satellites and spacecraft. These probability maps informed not only academic understanding but practical preparedness. Contingency plans, satellite maneuvering schedules, and public communication strategies all relied on these models. The comet, once an unpredictable visitor, became a quantifiable, analyzable entity. Visualization also proved indispensable. 3D models and simulations allowed scientists and policymakers to see the comet's trajectory in context, relative to Earth, other celestial bodies, and spacecraft in orbit. Animated renderings highlighted rotation, flaring events, and fragmentation in real time, bridging the gap between raw data and intuitive understanding. These visual tools were also critical for communicating complex information to non-specialists, ensuring that decisions could be informed, rational, and timely. Beyond immediate trajectory and risk, analysis extended to behavioral interpretation. Scientists examined historical records of similar comets, looking for patterns in flaring, fragmentation, and orbital deviation. They considered the comet's likely origin, how long it had traveled, and what forces it had encountered. Understanding its history provided context for its present behavior and suggested potential future changes. Patterns across decades of cometary observation revealed that no two objects behave exactly alike, but statistical commonalities could guide predictions and risk management. Finally, the human element of interpretation was paramount. Machines and algorithms could process vast quantities of data, but expert judgment remained central. Experienced astronomers assessed anomalies, weighted uncertainties, and made decisions about observational priorities. Interdisciplinary collaboration between physicists, engineers, statisticians, and communication experts ensured that the comet's story was interpreted accurately and that decisions reflected both scientific rigor and practical foresight. By the end of this stage, the comet had been transformed from a mysterious, almost unknowable visitor into a carefully analyzed and understood phenomenon. Its path, composition, behavior, and potential risks were charted. Every flare, every jet, every fragment had been accounted for. Humanity's gaze into the cosmos was no longer passive. It was active, intelligent, and coordinated. The comet's journey, once a fleeting curiosity, became a lesson in observation, interpretation, and the extraordinary capabilities of human ingenuity. The comet had been observed, tracked, and analyzed in extraordinary detail. Yet all that work could only reach its full impact if communicated effectively. In the realm of planetary defense, information is as vital as instrumentation. A cosmic visitor, flaring unpredictably, could stir curiosity, concern, or even panic. It was the role of scientists, journalists, and space agencies to deliver truth with clarity, to translate terabytes of data into comprehensible narratives, and to maintain public trust without sensationalism. The first principle of communication was accuracy over drama. Every headline, statement, or press release needed to reflect what was known and what remained uncertain. The comet's unpredictability made this challenging. While data predicted safe passage, flaring and fragmentation created variables that could alarm non-specialist audiences. Communicators had to carefully explain probability, risk, and behavior in ways that educated rather than terrified. Misrepresentation could cause undue panic. Understatement could lead to complacency. Balance was essential. Transparency formed the second pillar. Space agencies shared real-time data, simulations, and observational imagery, allowing independent scientists and even amateur astronomers to verify findings. Public dashboards, open-access orbital plots, and periodic briefings created a sense of collective observation. When people could see for themselves, watch a live orbit simulator, examine thermal maps, or track light curves, trust deepened. Transparency also countered misinformation, a persistent risk when cosmic events capture public imagination. Narrative framing was equally important. The comet's story was told as part of a broader cosmic context, emphasizing humanity's place in the universe, the marvel of observation technology, and the collaborative effort that made monitoring possible. By framing the comet as a natural phenomenon being studied and understood, rather than a mysterious threat, communicators encouraged curiosity and engagement without fear. Audiences were invited to witness science in action, to see behind the curtain, and to appreciate both the stakes and the triumphs of planetary vigilance. A carefully structured information hierarchy ensured messages were digestible. Initial alerts focused on essential facts, trajectory, nearest approach, expected visibility. Subsequent updates layered in complexity, thermal data, compositional analysis, fragmentation probabilities, and predictive models. By pacing the delivery of information, audiences were guided from simple awareness to nuanced understanding, reducing confusion while fostering engagement. This approach mirrored best practices in crisis communication, where clarity, transparency, and pacing are critical. Visual communication tools amplified understanding. High-resolution images, annotated simulations, and interactive dashboards allowed audiences to see the comet's position, motion, and behavior in real time. Animations depicted flaring events, rotation, and trajectory shifts, translating abstract numbers into intuitive, observable phenomena. For journalists, educators, and science communicators, these tools provided a bridge between technical analysis and public comprehension. Visual storytelling became a language that transcended jargon. Consistency in messaging was another cornerstone. Conflicting statements from different agencies or experts could erode trust quickly. Coordination between space agencies, scientific institutions, and media outlets ensured that updates were synchronized, verified, and accurately reported. When uncertainties arose, for example, minor deviations in trajectory or unanticipated flares, these were communicated openly, along with explanations of their significance and potential impact. This honesty strengthened credibility and encouraged informed engagement rather than speculation. Engagement extended beyond reporting facts. It involved educating the public about underlying science. Short explainer videos, infographics, and online forums introduced audiences to orbital mechanics, spectroscopy, and thermal mapping. By understanding the methods behind the monitoring, people appreciated the rigor and reliability of predictions. Education transformed passive viewers into informed participants, building a community that valued science over sensationalism. Media relations were carefully managed. Press briefings, interviews, and live streams provided a direct channel for experts to address questions and concerns. Communicators anticipated common misconceptions and prepared clear, evidence-based answers. For example, explaining why the comet posed no imminent danger required both scientific clarity and empathetic delivery, recognizing that fear often arises from uncertainty and unfamiliarity. Social media strategies were adapted to the unique challenges of a planetary event. Platforms were used to distribute updates, share simulations, and counter misinformation quickly. Short, digestible posts directed audiences to authoritative sources, ensuring that viral rumors were addressed before they could spread widely. The immediacy of social media was leveraged not for panic, but for education and engagement. The comet also highlighted the role of global collaboration in communication. Observations came from multiple countries and institutions. Therefore, messaging had to accommodate diverse audiences, languages, and cultural contexts. Coordinated briefings, multilingual content, and region-specific updates ensured that information was accessible worldwide. This global transparency reinforced the idea that cosmic events concern all of humanity, and that shared vigilance strengthens collective security. Ethical considerations were constant. Communicators carefully avoided hyperbole, avoiding terms like monster or doomsday, while still conveying the comet's significance. The goal was to respect public intelligence, to treat audiences as capable of understanding complexity, and to foster trust in science and institutions. Ethical communication became a protective layer, preventing panic while maintaining engagement. Finally, communication strategies incorporated feedback loops. Public questions, amateur observations, and independent analyses were monitored and addressed. This two-way exchange ensured that the flow of information was not one-sided. Audiences felt heard and informed, while scientists gained additional insights from collective observation. Transparency, engagement, and responsiveness together formed a cycle that reinforced credibility and trust. By the end of this phase, the comet's story was not just about a fleeting celestial visitor. It was about humanity's capacity to observe, interpret, and communicate with clarity and purpose. The public had witnessed not only the comet itself, but the systems, expertise, and ethical principles that transformed raw data into understanding. Communication became a form of planetary defense, shaping perception, ensuring preparedness, and building a resilient relationship between science and society. The comet's passage left behind a blueprint not only for observation, but for responsible, transparent, and engaging public communication. In the vast theatre of space, where objects move in silence and uncertainty, the voice of informed humanity provided context, reassurance, and clarity. It proved that the universe's mysteries, no matter how intimidating, could be shared responsibly, understood collectively, and appreciated deeply. Through careful analysis, visualization, and transparent dialogue, the comet became not a source of fear, but a catalyst for trust, knowledge, and wonder. A reminder that even in the face of the unknown, clear communication lights the way.